Hello, everyone. Thank you for coming. My name is Oxana Kharitonova. I work for Cloudflare on the Linux kernel team. I have spent many years working with high-level languages, and some time ago, I switched my focus to low-level development and the Linux kernel. Today, we are going to talk about how we can replace the cryptographic libraries with the Linux kernel. We will see how it can be more convenient in some ways. We will see why it's more secure. And as aim of this talk is to give you practical examples, we will see some code snippet, how to integrate with Linux kernel, how to make cryptography with Linux kernel, written in Golang and Rust. So the quick agenda of this talk is we are going to talk about the basic of cryptography, about memory bugs, mitigation against memory bugs, Linux. We are going to cover two Linux kernel subsystems. The first one is Linux kernel key retention service, aka key store, and we will see Golang and Rust examples, how to integrate with this system. And the second one is Linux Crypto API, and again, Golang and Rust examples, how to integrate with the second one. And of course, your questions. So in the simple words, cryptography is a process of changing the plain text into the ciphertext by using some private data called cryptographic key. The cryptographic key is just bytes of random data. It needs to be protected, but at the same time, it accessed constantly. Because each time when you establish TLS connection, when you encrypt or decrypt data, you need the key. And thus, the private key, the cryptographic key, will be constantly in the process memory. And this is the hardest part to guarantee that the key won't be leaked. So let's take a quick look at the C code, which can show you how the key actually can leak. This C code contains three functions. The first one, main, entry point, and encrypt and logger function. And they just call sequentially, the encrypt logger function are called sequentially from the main function. If we compile and run this code, we can see that actually we printed our private key. But this wasn't our goal. If you come back to the code, we can see that private key, key, is a private variable of encrypt function. We wanted to print message variable, which again, private variable of logger function. And these two functions, they don't exchange any variables, they don't exchange any data, they're fully isolated. So how did it happen? If we look at process stack, we will see that at the top of it, we have our main function. When the main function calls encrypt function, it plays on the stack memory right after the main function. And the key payload also copied to the stack memory. When the encrypt function finishes its execution, the stack pointer comes back to the main function. And everything below the main function, the memory below main function, is marked as free and can be reused for another function. And in our case, it's a logger. But unfortunately, we forgot to initialize the message in the logger function. And at the same time, we forgot to zero the key in encrypt function after we stopped using it. And this is how it leaked. So the data from the previous call is still available in the process memory stack. And the next function just accessed it. These type of bugs are called memory safety bugs. This includes out-of-bound reads, out-of-bound writes, use after free, double free, uninitialized variables. And the main problem with these bugs, that they're exploited not just in theory, but in practice too. One of the world's highly impacted vulnerability was Heartbleed in OpenSSL. The OpenSSL library is widely used for TLS connection. And in Cloudflare, we experience it too. We have to revoke and reissue about 100,000 certificates, and it was painful. So far, we talked about bugs exploited in the C code. But what about memory-safe languages like Python, Go, Rust, where the language compiler provides additional checks for the memory boundaries? Look at the statistic. This is statistic for the Python language. And we can see that it still has some vulnerabilities. This statistic for the Rust vulnerabilities. Oh, yep, sorry, it wasn't me. It has less, but at the same time, we have unsafe Rust. And it means that all the code we have discussed so far has had Rust memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside it that doesn't enforce these memory safety guarantees. It's called unsafe Rust, and works just like regular Rust, but gives us extra superpowers. And Golang, again, a few vulnerabilities and unsafe package in Golang. Package unsafe contains operations that step around the type safety of Go programs. So I have three main questions for you. Do you trust your code? Anyone? No one? Okay. Do you trust the code of open source libraries? Again? None? Everyone works for security? Do you trust the Linux kernel? Okay, no one trusts nothing. The first mitigation, which we onboarded in Cloudflare after the hard bleed in OpenSSL, was to separate two processes. So we replaced one application with two. The first one is web server, and it's important when one of the processes is network-facing application. And the second one is key server. It's really small, it does only cryptography, and it contains our private key. And they communicate through some established API. And it's more secure because two different processes don't share memory by default. If the web server has some vulnerabilities, the key will never leak on the internet, because the key never leaves the key server. However, we weren't the first to onboard this principle. The well-known SSH agent does the same. The agent will never send a private key over its request channel. Instead, operations that require a private key will be performed by the agent, and the result will be returned to the requester. This way, private keys are not exposed to clients using the agent. But what if we replace the second application with the Linux kernel? We already have Linux as an operating system. We don't need to design, build, and maintain the second application. And it will be even more secure, because in this space, we completely move the key from the user space to kernel space. And to see how we can do it, we are going to talk about the first Linux subsystem, which is called Linux Kernel Key Retention Service, aka Key Storer. This is the system where the key provisioned, stored, and cached. It has two entities, keys and key rings, analogous to files and directories, respectively. So keys are files, key rings are directories. Keys can hold the actual cryptographic material. The key type determines which operation can be performed over the keys. For example, user key type, the payload of the key of user key type may be read update by user space application. The logon key type prohibit prohibit user space application read or update key payload. So user space application completely doesn't have access to the key of type logon, and asymmetric key used for public key cryptography. Key rings determine key lifetime and shared access. User key rings bound to the existence of particular user shared between all the processes of the same UID. Process key ring bound to some processes, thread, or session. It means if your application terminates, like normally or abnormally if it crashes, the key will be erased from the Linux kernel automatically, and none other application will access the key. Persistent key rings automatically cleaned up after an expiration time, and special key rings owned by the kernel. So how can we upload, read, update, search for a key in the Linux kernel? We can do it manually through their console using key control utility. Just type in console key control and some command, depends what we want to do with the key. Or we can use any programming languages which support system calls. For example, I made a screenshot of key control utility, and it lists all the functions which are supported by key control, and it means the Linux kernel has interface through the system calls for this function. And this means that we can implement any of this function or all of them in our high-level language, which supports system calls. Additionally, Linux kernel provides special service which called request key callback service, and it's specially designed for provision key. So it just script which written again in any languages. It can be Python, Rust, Golang, Bash, anything you like, and the location of the script is put in the key store, and when the key requested from the Linux kernel, it will be fetched by the script and cached in the Linux kernel. I will stop theoretical part about the key store here, as aim of this talk to give you some practical examples how we can integrate with Linux kernel key retention service, and I will show you some code snippet. The first one written in Golang. I would recommend you, so Golang provides the package called USENIX. You can use it. It provides integration with the Unix system calls. It already has predefined function for adding key to the Linux kernel. It's called Unix add key. It accepts 4 parameters. The first one is the key type, as we discussed, user logon asymmetric. In this example, I use user. Key name is just some string which you want, how you want to name your key. Key payload data, and the key ring where the key will be attached. In my example, it's process key ring. And in return, the Linux kernel return you serial of the key. It's identifier, unique identifier. It's just integer number. You can cache it in your application, but temporarily inside your process. Don't cache it on, don't write it on the file system, database, don't create constant for this integer number, because each time it will be regenerated when the key is expired or need to be provisioned again. So if your process terminates, the key will be erased from the Linux kernel and you need to request again. I will show you later how to request this serial. This function is read key payload from the Linux kernel. It doesn't have dedicated function in the Unix package, but we can easily implement it with system call. So we provide that the system call is key control read, serial, and buffer where we want to read our key payload. And the last row, it actually shows you how to request key serial, because all the operation which we will be doing over the key, like encryption, decryption, is are based on the serial number of the key. So to request the serial number of the key, you need to provide again key type, key name, and key ring, and these three arguments can be hard-coded in your code. Now let's take a look at the Rust examples. It will be the same code, the same algorithm, but implemented in Rust. For Rust, I would recommend you using libsecrate. It's very, very similar what would you write in C. It doesn't has dedicated function like Golang package has, but at the same time you can implement anything, just standard using standard system call, and this function for adding key. So the system call sees that key, again, user type, key name, payload, and type of the key ring. And one caution that in Rust you need to, the C code and Linux, they work with strings, null terminated strings. So you either need to add the null terminated byte at the end of the string by yourself, or use special Rust function. This function for the read key, I couldn't fit it in one slide, so it's split in two. Everything similar to Golang. Again, key control read syscall, serial number, and the buffer where the key will be read. We just integrated our application with the Linux key store. The key store allows you to read, update, write the key, but it doesn't do any cryptography operation for you. It's just storage for the key. So we still need our key if we do cryptography inside our application. It's still better than have your key written on the file system or in database, because in this way you can request the key each time when you need it, and it will be limited to the process or user ID which is attached to key ring. So if your process terminates, crash, the key will be erased automatically from Linux, and it wouldn't be accessed from any other processes. But our goal is to come to this scheme where we have application on one side which doesn't do any cryptography operations, which doesn't contain the private key, and the Linux on other side, which does all the cryptography for us. To implement this scheme, we need to introduce the second Linux subsystem. It's called Linux Crypto API. All supported algorithms which we, with the required parameters, can be found in ProCrypto. So before starting implementation, you need to check ProCrypto, find the algorithm, crypto algorithm which you are going to use in your application. There can be different implementation of the same crypto algorithm. In this case, the name will be the same, but the priority will be different. And the driver name will be unique. If you request the algorithm based on the name, then the Linux kernel will pick the one with the highest priority, or you can pick it directly based on the driver name. In my examples, I'm going to use AES CTR 128. AES stands for Advanced Encryption Standard. Is a symmetric key algorithm, meaning the same key is used for both encrypting and decrypting the data. CTR is the mode. Without the mode, the same plain text would produce the same ciphertext, and this is what we don't want in cryptography. And the numbers 1 to 8 is the length of the key. The length is 128 bits or 16 bytes. In our procryptor, this algorithm is represented by this block. So we have name ctr_is. We will using the type is just additional parameter for the Linux. It's SK cipher, means symmetric key cipher. The key size can be minimum 16 bytes and maximum 32 bytes. For this type of algorithm, the key can be 16, 24, or 32 bytes. And IV size is, IV is initialization vector. It must be 16 bytes. So IV, it's again, random bytes of data. And now let's take a look in the actual code examples, how you can integrate the Linux Crypto API with your application written in Golang. Firstly, we need to predefine the structure, just requirements from the Linux kernel integration. So the IV initialization vector needs to be provided through this structure. It has IV length and it has IV value. This is crypto function, and on the right side, I quoted the official Linux kernel documentation, how to integrate with the crypto API. On the left side, I put the words from the documentation into Golang syntaxes, into Golang words, and this is what we have. This function is crypto. It can be used for both encryption and decryption operation. I will show you on the next slides how to change the type of operation. So with the first step, we need to create a socket of type AFLG. So the first row we're creating the socket. After we provide two parameters. The first one is the type, which I showed you in file procryptor, and the name of algorithm. I'm using the name, not the driver name. And this is a specific algorithm parameters which are different for different algorithms. After, with the second step, we need to bind on this circuit, what we are doing. And the final step, we need to involve accept a system call. And the file descriptor, which is returned on this system calls, will be used for the operation like encryption, decryption. But before accepting this system call, we also provide key payload. It's not quoted on the right side. It still exists in the kernel documentation. You can find this, but it's specific to the algorithm which you are using. So we provide the key based on the actual key material. And further, I will show you how to replace the key material with the serial number, which can be fetched from their key store, because we want to eliminate the key from the user application. Further, we need to provide two additional parameters. They're called auxiliary data. The first one, type of operation. In this case, it's encryption. So if you want to use apply decryption, you use the same function, the same code. You just change the type of operation and you replace the plain text, ciphertext, vice versa, what you're going to send to the Linux kernel. So these two auxiliary parameters, the first one is type of operation, are provided through the structure C-message header. Again, it's from the kernel requirements. You just fill this structure. After you set the IV, again, through the same structure, and we are ready to exchange data with the Linux kernel. So we are sending plain text, and we are getting ciphertext in response. And this is how to provide, instead of providing the key payload as we used in our function, we should replace key payload with key serial. It's a different socket option. So we said that the key needs to be fetched with the Linux key store based on this serial. And that's all for Golang. Let's take a look at Rust. The Rust code is very verbose, but the good news, it's very, very aligned with the C code, which I already have in my blog post. So you can take a look, and basically you will implement one-to-one in the Rust language. I still give you some code snippet to simplify your life. The approach is the same. We involve few system calls. The first one, we set up socket, IFLG socket. After we provide two parameters, SK cipher and algorithm. I'm using driver name instead of algorithm name. After we bind on this socket, we set the key based on the serial number, and we accept socket. And for the step, we need to provide two parameters through auxiliary data, like we did for Golang, and exchange data between Linux kernel. Linux crypto API varies. Not all the crypto algorithms are supported by crypto API, so you have to check proc crypto. It might be slower, as it adds additional overhead for the system calls and copying plain text, ciphertext from user space to kernel space. Instead of copying data, zero copy interface can be used, but it's limited up to 64 kilobytes. It means that instead of copying data from user space to kernel space, you just transfer the file descriptor from the user space, and the kernel can read the data from the user space. We compared with OpenSSL. The crypto part is almost the same, but because of overhead on system calls, it's almost 2 times slower. So the whole operation is 2 times slower. With Golang and Rust, might be different outcome, because it depends which user space library you're using, how it's optimized, how it's implemented. There is also can be optimization based on the language compile. So you have to compare yourself. But it's more secure than any user space library, because if you have vulnerability in your application, the key will be in the kernel space, and it will not be leaked. There is some useful links. You can find more details about what I was talking today. There's a couple of blog posts. And thank you very much.